If you haven't already watched the first video in conservation of energy that's titled Conservative Forces in Energy Conservation, you should watch that first. Well, if you have, then here is just a summary of some important points from that video. The total energy of a system can change only by amounts of energy that are transferred to or from the system. So if we have a system that is isolated from its environment, then the total energy of an isolated system cannot change. Now, it can change internally from one form to another, such as from kinetic to potential, but the total amount will stay the same. So in a situation where there are no external forces that do work and there are no non-conservative forces, then we can apply conservation of mechanical energy, which is kinetic plus potential. And thus we have the change in kinetic energy plus the change in potential energy equals 0. Another way we could write this is that the total mechanical energy at one time will equal the total mechanical energy at another time. So we can use this to solve many motion problems. So if there is friction, then we only need to add another term, which is the increase of thermal energy because of the work done by friction. And if there are external forces that do work, then we just add the appropriate term to account for that. So if there are external forces that do work, then the work done by the applied external force equals the change in the mechanical energy, which is delta K, which is change in kinetic energy, plus delta U, which is change in potential energy. If friction is involved, we just add a term for the increase in thermal energy because of the work done by friction. So we have delta K plus delta U plus delta E thermal equals 0. And then if there's an applied external force doing work on our system, then that applied external force will equal the change in kinetic plus change in potential plus delta E thermal. Where again, the increase in thermal energy, the delta E thermal, is equal to the positive value of the work done by friction. Remember, friction does negative work on our system, which means that we'll have an increase in thermal energy equal to the positive value of the work done by friction. All right, let's look at a simple example here. We have a box of mass m that slides across a frictionless table with a speed v. It then runs into a spring of force constant k, where it compresses the spring and momentarily stops. In terms of the given initial conditions, the mass, the speed, and the spring constant, how far is the spring compressed? All right, so think about this. Think about how the energy changes and if we have any external work or anything like that. And then think about how you might solve this problem. All right, so we don't have any friction, so there are no non-conservative forces, and there are no external forces. Our system consists of the block and the spring, and so there's nothing else external to the system that will do any work. So that means the total mechanical energy will be conserved. So what are we doing? We start with kinetic energy, the moving block, and then the block will compress the spring and momentarily come to a stop. At that point, all the energy will be potential energy stored in the spring. So we have the change in the kinetic energy plus the change in the potential energy equals 0. Well, the final kinetic energy is 0. The initial kinetic energy, 1/2 mv squared. So the change in the kinetic is just minus 1/2 mv squared. The potential energy, final potential energy, is 1/2 kx squared, where x is the amount the spring is compressed, and the initial spring potential energy, of course, is 0. So the spring potential energy increases by 1/2 kx squared. So we have 1/2 kx squared equals 1/2 mv squared. Final spring potential energy equals initial block kinetic energy. And then we can solve for x. So the halves divide out, and solving for x, we get the square root of mv squared over k. So that's the solution. All right, here's another example. we have a small block of mass m that can slide without friction on the loop-the-loop track as shown. What is the minimum height h that the block can be released so that the block does not lose contact with the track around the loop? So we want to let the block be released from a height great enough so that it can make it through the loop without falling. All right, so see if you can solve this one. So pause the video and try to solve this problem yourself before moving on and looking at the solution. All right, so one thing we notice, we don't have any friction, so there are no non-conservative forces, and there's no external force. We just have gravity in our track, our frictionless track. Now, in order to make it through the loop, we have to be going fast enough. So if you recall, we did a problem similar to this when we were talking about centripetal force. And there's a video in the section on centripetal force that talks about this. There we determined how fast it has to be going so that it doesn't lose contact with the track at the top of the loop. So once we know that speed that we have to make it through the loop without falling, then we can relate that speed to the height by using conservation of mechanical energy. So let's look at the minimum speed that we have to have at the top of the loop so that it doesn't lose contact with the track and doesn't fall. Well, I have a free body diagram shown below the track here with the block at the top of the loop. When it's at the top of the loop, we have the weight force down and we have the normal force from the track pushing the block into the circle. Those two forces are both down and the block is moving in a circle, so that means the sum of the forces equals m times the centripetal acceleration, which is v squared over r. So we have the weight mg plus the normal force equals mv squared over r. The smallest speed is just when the normal force goes to 0. So that's the minimum speed we must have to make it through the loop. So we set the normal force equal to 0 and we get mg equals mv squared over r. The m divides out. Solving for v, we get the v minimum speed must be equal to the square root of rg. So the speed to make it through the loop must be greater than or equal to the square root of rg. All right, now we can use conservation of energy to relate that speed at the top of the loop to our initial height, h. All right, so now we use conservation of energy to relate the speed at the top of the loop to the height, h. So we have the change in the kinetic energy plus the change in the gravitational potential energy equals 0. Our final kinetic energy, 1/2 mv squared. The initial, of course, is 0 since we're releasing the block from rest. Now, the potential energy is going to change. Initial is mgh, and then when it reaches the top of the loop, it will still have some potential energy relative to the ground, which would be mg times 2r, where 2r is twice the radius of the loop, so that would be the height at the top of the loop. And then those two quantities then will sum to 0. So we replace the v squared with rg. That's the minimum speed we must have to make it through the loop. So we replace the v squared with rg. So I've got 1/2 mgr plus 2 mgr minus mgh equals 0. The mg divides out because we have an mg in every term. So I get a 1/2 r plus 2r, which is 5/2 r, will equal to the height h. So that's the minimum height we need to release the block so that it will make it through the loop without falling. All right, here's a vertical spring example. We have an 8-kilogram stone rests on a spring, compressing the spring by 10 centimeters. A, what is the force constant K of the spring? Part B then, the stone is pushed down an additional 30 centimeters and released, launching it up into the air. What height above the release point does the stone reach? So again, see if you can solve this problem yourself. Pause the video, think about the energy changes, and notice there are no non-conservative forces involved. So we can apply conservation of energy. Well, to apply conservation of energy, we need to know the spring constant. Well, the initial conditions allow us to find the spring constant. So we have the 8 kilogram stone rests on the spring and compress it by 10 centimeters. And so that means it's in equilibrium since it's at rest. So when it's in equilibrium, we have the weight pushing down and the spring force pushing up. Those forces must sum to 0. So we have Ky1 minus the weight down equals 0. Well, y1 is, of course, the 10 centimeters the spring is compressed. And so for that, we can solve for K, the spring constant, equals mg over y1. Well, the mass was 8 kilograms. G, of course, is 9.8 meters per second squared. And y1 is the 10 centimeters, which is 0.1 meters. And we get a spring constant of 784 newtons per meter. So we needed that value in order to solve part B. All right, now to solve part B, we can apply conservation of mechanical energy to the stone spring earth system. We don't have any non-conservative forces acting, so that means our mechanical energy will be conserved. So we are just turning spring potential energy into gravitational potential energy. So let's write the equation for conservation of mechanical energy. All right, so from conservation of mechanical energy, we have change in kinetic plus the change in spring potential energy plus the change in gravitational potential energy equals 0. Well, we don't have to worry about the change in kinetic energy because when we initially push it down the additional 30 centimeters, the stone will be at rest, and when it reaches its maximum height, it will be momentarily at rest there as well. So the change in kinetic energy we can just write as 0. We don't need to worry about the kinetic energy in between. We're only concerned with our initial condition and our final condition. So initially, we have some spring potential energy. Once the stone is in the air, the spring is no longer compressed, so there's no spring potential energy. So the spring potential energy is going to be decreased by 1/2 K times the total distance it's compressed squared, which is y1, the 10 centimeters, plus y2, the additional 30 centimeters. The gravitational potential energy is going to increase by mgh. And we'll just say the initial is 0. So I have mgh equals 1/2 K times the quantity of y1 plus y2 squared, where again, y1 was the 10 centimeters and y2 is the additional 30 centimeters. Solving for h, we get K over 2mg times the quantity y1 plus y2 squared. Now I plug in the numbers. K was 784 newtons per meter. And in the denominator, we have 2 times the mass, 8 kilograms, and G 9.8. And y1 plus y2 is 40 centimeters or 0.4 meters squared. And when we crunch all those numbers, I get 0.8 meters or 80 centimeters. So now we have the solution. All right, let's look at something that has friction. So here in the diagram, we have a block that can slide along a track and descends a vertical distance h. The track is frictionless except for the lower section where we have friction over a distance d. And the block will slide to stop in the distance d because of the friction down there. Now, let's think about this conceptually first. A, if we decrease the height h, will the block now slide to a stop in a distance that is greater than, less than, or equal to d? And then part B, instead, if we increase the mass of the block, will the stopping distance now be greater than, less than, or equal to d? So think about these things. All right, so if we decrease the height, then the initial mechanical energy will be much smaller. So it will slide to a shorter distance. Right, so we have less energy to begin with, and so it will slide to a stop in a shorter distance. Now what about part B? Think about that one. All right, so for part B, it says we're going to increase the mass of the block. Does that change the stopping distance? Well, actually, it does not. You would think that with more mass, that we'd have more energy. Well, we do, but we have more initial gravitational potential energy because of the increased mass, but the work done by friction also depends on that same mass. So when we solve for the distance, the mass will divide out. All the terms will have the mass in it, and the mass will divide out. All right, now part C. If the block starts from rest at the edge of the hill, given the height h and the distance it comes to a stop d, find the coefficient of kinetic friction. So we're just applying conservation of energy, but now we have an additional term because of the increase in thermal energy for the work done by friction. So we have change in kinetic plus change in potential plus delta E thermal equals 0. The change in the kinetic energy, of course, is 0 since we start at rest, and when we finish, we're at rest. We don't have to think about the kinetic energy in between, only our initial and final conditions. So delta K, of course, is 0. The potential energy is going to decrease by mgh. So delta U is minus mgh. Delta E thermal is the positive value of the work done by friction, which is just the frictional force times the distance it takes to stop. And so those sum to 0. So we have the frictional force times the distance equals mu sub k times mg times the distance, right? Remember, frictional force, kinetic friction is equal to mu sub k times the normal force, which in this case is mg. So mu sub k mgd equals mgh. Notice the mg is on both sides and it divides out. So the coefficient of kinetic friction, mu sub k, was equal to h over d. So again, you can see that in part B, increasing the mass doesn't change the distance it takes to stop. The mass is in both of those terms and it divides out. All right, so that's the end of this video. I'll do another video and we'll do some more conservation of energy examples. But for now, we'll just take a break here. So please click on the like button. Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel and please subscribe. I hope you find my videos useful.